Hello everyone. In the previous session, we have started classification of discrete time signals depending on their characteristics, and we discussed about deterministic and non-deterministic signal. We also discussed about the differences between causal, anti-causal and non-causal signals with some examples. In this particular session, we are going to discuss one more very important topic of signals and system, that is symmetric and antisymmetric signal, which is also called as even and odd signal. Okay, so let's start. So basically, a discrete time signal is said to be symmetric or even if x of minus n is equal to x of n for all values of n. But a discrete time signal is said to be antisymmetric if x of minus n is equal to minus of x of n for all values of n. So if this particular condition satisfies, then I can say that the signal is an even signal or symmetric signal. And if this particular condition satisfies, then I can say that the signal is an odd signal. Now, if either of these conditions are not satisfied, then I can say that particular signal is neither even nor odd. Now, point number 2, a symmetric signal is always symmetric about the y-axis, or you can say the amplitude axis. So we can say that it is a mirror image about the y-axis of a signal. Now, an antisymmetric signal is always symmetric about the origin, which is called origin symmetry. So we will see what exactly a amplitude symmetry or y-axis symmetry, and we will also see what exactly a origin symmetry. So here are some examples of symmetric signals or even signal. X of n is equal to cos omega naught n is the best example of even signal because it is symmetric about the y-axis. Now x of n is equal to sin omega naught n is a best example of odd signal, or you can say antisymmetric signal. Okay, this is symmetric about the origin. The next example under symmetric signal is x of n is equal to n square, and you can say even power of n. X of n is equal to n cube, and you can say that odd power of n are always antisymmetric or odd signals. So we will understand about this concept with the help of graph also. So as you can see on the screen that x of n is equal to cos omega naught n has a graph like this. This is my time axis, this is my amplitude axis, and you can see this is a discrete time signal of cos omega naught n. And you can see when you put a mirror on y-axis, the image, the exact replica of positive x-axis can be seen on the negative x-axis. So that is why this particular signal is called as even signal. So the above signal is symmetric about y-axis, or you can say amplitude axis. That is why this particular signal is called as even signal. Now this one you can see x of n is equal to sin omega naught n has a graph like this. Now the moment you put a mirror on the y-axis, you will not see the exact replica of positive x-axis in the negative x-axis. So basically you can see the signal which you can see in the first quadrant, the same signal you can see in the third quadrant with opposite amplitude. So this is what we call origin symmetry. So if any signal satisfies such type of condition, then I can say that particular signal is an odd signal. Now this is the best example of an even signal. As you can see, this is the graph of x of n is equal to n square. We can see that for any value of n, it may be a positive value, it may be a negative value, n square will always be a positive. So you can see when I put n equal to 1, n square will be 1. When I put n equal to 2, n square will be 4, positive 4. So for positive value of time, I am getting the positive amplitude. Now for negative value of time, such as I am putting minus 2 to the power 2 is plus 4. So for negative value of time also I am getting positive amplitude. So this particular signal is an even signal. If you put a mirror on the y-axis, the exact replica of the positive x-axis samples can be seen on the negative x-axis. Now x of n is equal to n cube is the best example for odd signal. As you can see, we have the signal in this first quadrant for positive value of time, and we have the same signal in the third quadrant for negative value of time. So the amplitude which you can see in the first quadrant has the same amplitude in the negative in the third quadrant but in opposite direction. So this is what I call a origin symmetry. So we can conclude that in any signal, if the power of n is odd, then that particular signal is always an odd signal. And in the same way, if the power of n is even, then that particular signal is always an even signal. So as we discussed already, what are the even signal, what are the odd signals? We have also seen few of the examples. In this particular slide, we will see if a particular signal is given, then how to dissociate that particular signal into its even and odd part. Okay, so let us see. Any discrete time signal x of n can be represented by the summation of its even part x even n and odd part x odd n as shown below. So in equation number 1 you can see x of n can be represented by the summation of x even n and x odd n. Now what will be the value of x of minus n? X of minus n is equal to x even of minus n plus x odd of minus n. Now we know that x even of minus n is always equal to x even n, and x odd of minus n is always equal to minus of x odd n. So this will be my second equation. So this is my first equation for x of n. This is my second equation for x of minus n. Now add equation number 1 and equation number 2. So x odd n and x odd n will be cancelled out, and we will be having x even n equal to x of n plus x of minus n divided by 2. So this is how we can calculate the value of x even n. So this is the formula for x even n. Now the moment I will subtract the equation number 1 and equation number 2, x even n and x even n get cancelled out, and we will be having x of n minus x of minus n divided by 2, which is x odd n. So this is how we can calculate the value of x odd n. So basically, if we need to dissociate a particular discrete time signal into its even part and odd part, then we need the original signal x of n and the folded version or the time reversal signal of x of n. So let us solve few of the examples based on this particular concept. Determine the even and odd part of the signal shown below. Each question carries 2 marks for semester examination, and this is also very important for gate examination. So the first signal is x of n equal to a to the power n. The second signal is 2e to the power j pi n by 3. And the third signal is 4, minus 4, 2, minus 2. So these are the 3 discrete time signals given over here, and we need to determine the even part and odd part from the given discrete time signal. So let's solve one by one. So x of n is equal to a to the power n. The even part can be calculated as x even n is equal to x of n plus x of minus n divided by 2. So x of n is equal to a to the power n, and x of minus n will be a to the power minus n. So x even n will be a to the power n plus a to the power minus n divided by 2. So even part is over. Now odd part can be calculated as x odd n is equal to x of n minus x of minus n divided by 2, which is equal to a to the power n minus a to the power minus n divided by 2. So this is the even part and odd part for this given discrete time signal. Let us move to the second example. X of n is equal to 2e to the power j pi n by 3. Now any exponential function can be represented by its equivalent trigonometry function according to the Euler formula, or you can say Euler theorem. So x of n is equal to 2 cos pi n by 3 plus j 2 sin pi n by 3 is the trigonometric representation of this given exponential. Now what will be the value of x of minus n? It will be 2 cos pi n by 3 minus j 2 sin pi n by 3. Now the even part can be calculated as x of n plus x of minus n upon 2, and odd part will be x of n minus x of minus n upon 2. So x even n is 1 by 2 cos pi n by 3 plus j2 sin pi n by 3 plus 2 cos pi n by 3 minus j2 sin pi n by 3. Now j2 sin pi n by 3 and minus j2 sin pi n by 3 get cancelled out. We have 2 plus 2, 4 times of cos pi n by 3 divided by 2, which is ultimately 2 cos pi n by 3 x of, so this is my even part. Now let us find out the odd part. 1 upon 2 whole into 2 cos pi n by 3 plus j2 sin pi n by 3 minus 2 cos pi n by 3 plus j2 sin pi n by 3. Now this time 2 cos pi n by 3 and minus 2 cos pi n by 3 get cancelled out, and we have 4 times of j sin pi n by 3 divided by 2, which is j2 sin pi n by 3, and this is my odd part. Just by looking at this particular equation, we can also find out which one is the even part and which one is the odd part. As we discussed already that all cosine functions are always even function, and all sine functions are always odd functions. So as we know that 2 cos pi n by 3 is an even function and j2 sin pi n by 3 is the odd function. So this is my even part and this is my odd part. But if this question has been asked in semester examination, then we have to solve with the procedure. Okay, next question is x of n equal to 4, minus 4, 2, minus 2. Now even part x even n is equal to x of n plus x of minus n upon 2, and odd part is x of n minus x of minus n upon 2. Now this is my x of n, which is the original signal, and this is x of minus n, the folded signal, or you can say time reversal signal. So as we know that for a time reversal, all the samples in the right side of the origin will be shifted to the left side of the origin. So minus 4, 2 and minus 2 will be shifted here, and it is minus 2, 2, minus 4, 4 pointer at the last sample. So we can easily calculate the value of x even n by adding these two functions divided by 2, and odd part by subtracting these two functions divided by 2. This I am leaving as a task because we have already discussed in one of our lecture that how to perform the signal addition. Now here are a few assignment questions for the test of knowledge. X of n equal to n, x of n equal to n square, x of n equal to n cube, x of n equal to cos omega naught n, x of n equal to sin omega naught n, and last one is x of n equal to mod of n. So we need to basically find out the even part and odd part for the given signals. So this is all about symmetric and asymmetric signals. Thank you.